Welcome. We are in Unit 12, Logarithmic Functions, and today we look at Day 2, Properties of Logarithms. We are in 6.5 from the book, and we look at all the objectives. We will cover the entire section today. Let's talk about properties of logarithms. There are 5 properties that we will use again and again. Here they are. Here are the 5 properties. And these properties can be derived from the laws of exponents. So if we believe the laws of exponents, it's not too hard to establish these properties. So I'll first go through the different properties briefly and talk about why they are true. I'll give little justifications for them. But then we'll spend a lot of time looking at examples and working with these properties. So let's begin. We'll look at properties 1 and 2. These properties really come from the fact that my two functions a to the x and the log base a of x, these are inverse functions. So if I compose these functions, if I put one inside of the other, all I get back is x. So for example, if I take a and in place of the x I put log base a of x, then the answer has to be x. So I've put the log function inside of the exponential function. Well, that's exactly what I get in property number 1. A to the log base a of m is m. So that establishes property 1. For example, we might imagine maybe 2 raised to the log base 2 of 7. That equals 7. There we go. Now, what if I take these two functions again and I compose them the other way around? I'll start with log base a of, and inside of that I put my exponential function, a to the x. So I will get out x. And that's exactly what happens here in property 2. For example, we might say log base 3 of 3 to the 10, that equals 10. Properties 3 and 4 are really interesting. Look at property 3. The log of a product of numbers is a sum of the two logs. This is exactly the opposite of exponentiation. There's this rule of exponents that says a to the m plus n equals a to the m times a to the n. Look what's happening. This property is maybe a little more familiar to us, but we start off with a sum of numbers, and that becomes a product of two exponents. So you see how that's the opposite of what's going on here. In logs, I have a product of numbers, and that turns into a sum of logarithms. So let's see why that property holds. Here's what we do. Now, this is kind of a long, complicated line of equalities, but we'll take them bit by bit. So the first thing I do is I'm going to take the left side of the property I want to establish, and I make that the exponent of a. And so now my expression is a raised to the log base a of mn. And here's where property 1 comes in handy. I've written it down here. Did you even notice it was down there? But I want to be sure we recognize that, and we're going to use that a lot. So by property 1, so here we go, property 1, a raised to the log base a of mn is mn. Now let's apply property 1 again just to the m. And so m is the same as a raised to the log base a of m. And I can also apply it to the n. And n is the same as a raised to the log base a of n. Okay, so again, I used property 1 to make that equality work. But now, I just use a law of exponents. Here I have that a to the m times a to the n equals a to the m plus n. So my base is the same in both cases. I have a as a in the base. And so my exponents will add together. My exponents become log base a of m plus log base a of n. So what have I established? Look at the left-hand side and look at the right-hand side. Both of these have the form a to the something, and I know that a to the x equals a to the y if and only if x equals y. Here's another property of exponents. If two exponential expressions have the same base, then their exponents must be equal. And so, looking at the exponents of the left-hand side and the right-hand side, it must be the case that property 3 holds, because that's exactly what I have up there. There's the exponent of the left-hand side and the exponent of the right-hand side. All right, so here it is, just in some more words. Since a to the x equals a to the y, if and only if x equals y, the property follows. Let's look at property 4. We have a very similar proof, again using this property 1 a lot. Let's say I start off with a raised to the log base a of m over n this time, and by property 1, this turns into m over n. But then let's use property 1 in reverse for m, and that becomes a to the log base a of m, and for n in the denominator, a raised to the log base a of n. And now I use properties of exponents, and I can subtract those two. So look, the left-hand side is a raised to one thing, the right-hand side is a raised to another, so those two exponents must be the same. That is exactly property 4. The log base a of m over n is the same as log base a of m minus log base a of n. All right, how about if we put some actual numbers in these things? What do these properties look like when we use them? So property 3, we might have something like, I don't know, how about log base 2 of 15. Now I'm using the fact that 15 is 3 times 5, so I can write this is the same as log base 2 of 3 plus log base 2 of 5. Do you see that? See how that works with property 3? For property 4, how about something like log base 3 of 2/7. And that will be the same as log base 3 of 2 minus log base 3 of 7. There we go. So it kind of simplifies it a little bit. It's nice to get rid of those fractions and just turn it into subtraction. Property 5. I like this property a lot. So log base a of m to the r equals r times log base a of m. It's like this r in the exponent has traveled in front to become a multiplier in front. So why is this true? Well, the proof is actually very similar to the ones before. Take the left-hand side and make it the exponent of a. So a raised to the log base a of m to the r. Now use that property 1, and this is just m to the r. Now the m, use property 1 to rewrite the m as a to the log base a of m. And this r hangs around, it stays outside. And now I use another property of exponents. Let's see, it's this a to the m raised to the n. We multiply exponents, so that becomes a to the n m. So in the same way, a to the log base a of m, all of that raised to the r, that becomes a raised to the r log base a of m. And look at this, I compare my exponents, there and there, and those exponents must be equal, and that is exactly property 5. So for example, let's say log base 5 of 2 cubed, that's the same as 3 times log base 5 of 2. All right, let's do a lot of examples. How about simplifying? Simplify. Oh, and I should say, for all of these examples, please be honest with yourself, challenge yourself, pause the video before I do them. I'm just going to go through and solve these examples, but you will get so much more out of these examples if you pause the video and really give them a try yourself before I do them. All right, let's begin. Number 1, simplify. Log base 10 of 5 plus log base 10 of 2. Oh, okay, well it's going in the opposite direction of the property we looked at earlier, but we can work this out. That's the same as log base 10 of 5 times 2. which is log base 10 of 10. And now, what's this? It looks like it ought to be simplified, right? In fact, it is. It's easily simplified. Think about this 10 on the inside as 10 to the 1. Log base 10 of 10 to the 1 is just 1. In fact, in general, log base a of a equals 1. Because it's like, previously I had an x up there and the answer was x. But if x is 1, then it just becomes 1. So log base a of a is 1. Just a nice little fact to tuck away. Number 2, simplify log base 6 of 2 plus log base 6 of 9. All right, so how about that becomes log base 6 of 2 times 9, and that's 18. Log base 6 of 18. And I could stop there. I have combined the two logs together, but that 18 has a factor of 6, which is interesting. Let's see what happens if I start playing around with that factor of 6. So I can write this log base 6 of 6 times 3. That makes me want to separate those out again, right? So maybe this is log base 6 of 6 plus log base 6 of 3. And now I can use the fact that I established earlier. Log base a of a is 1, so log base 6 of 6 is 1, and I end up with 1 plus log base 6 of 3. There we go. That looks simpler. Examples 3 and 4. Pause the video, give these things a try. All right, first one, number 3. Let's simplify these two guys. Okay, it's subtraction this time, so I'll be dividing. So log base 5, and it's important, make sure they have the same base. The properties don't work if they don't have the same base. 3 over 15. Oh, okay, well that fraction reduces. That's log base 5 of 1/5. And that 1/5, that reminds me, that's log base 5 of 5 raised to the negative 1. Look at that. That whole thing equals negative 1. All right, number 4. Let's start by simplifying the exponent. So I still have 9 in the base. But what about that exponent? Log base 9 of 2 minus log base 9 of 7. That turns into a division. That becomes log base 9 of 2 over 7. And so the answer has to be just that 2/7. Examples 5, 6, and 7. Let's work with e and natural log. Remember, natural log is just a log with a base e. So natural log of e to the 8, well, that's really simply 8. Right? And how about this next guy? E to the 4 times the natural log of 3. Well, I know how to handle e to the natural log of 3. That would be nice. Oh, but in fact, I can see that this whole thing looks like e to the ln 3 raised to the 4th. Inside the parentheses, that thing just becomes 3. So I have 3 to the 4th, and I get 81 there. Number 7, how about if I simplify this? Okay, well I have a product inside, so the product turns into addition. In this case, I have an addition of the natural log of 5 plus the natural log of e. And the natural log of e, do you know what that is? That's just 1. So my simplification becomes natural log of 5 plus 1. Moving along, example 8. Here are some things with division. So division on the inside of log tells me I'm going to change it into a subtraction. So how about natural log of e to the 7 minus, and I just have another variable k here, but that's okay. It could be a number, it can be a variable, that's fine. Natural log of k. And this simplifies a little bit. How about 7 minus the natural log of k? Number 9, okay, again I have a division, so this becomes log base 2 of k minus log base 2 of 8. And it looks like that might be the end, but but it's not. Do you recognize that 8 as something? How can I simplify log base 2 of 8? Well, 8 really equals 2 cubed. So let me take that 8 out, and I'll write 2 cubed in there instead. And now we can see that this simplifies to log base 2 of k minus 3. There we go. A few more, we'll start introducing x's as a variable inside of our log problems. Oh, and we also see the first appearance of property 5. We have an exponent here, that's 7. So what does property 5 tell us? This whole thing just becomes 7 times log base 10 of x. There we go. How am I going to simplify this middle one? Well, the square root of x, remember, so this is log base 3. That square root of x is the same thing as x raised to the 1/2 power. So now, property of logs, I can take that 1/2, bring it out front, and this becomes 1/2 log base 3 of x. There we go. This last one, let's combine the two logs. It's a subtraction of logs, so I'll take a division of their arguments. So that's log base 2 of x squared plus x all divided by x. And it looks like the top and the bottom, they have a common factor of x. And I know that x isn't going to be 0 because 0 is not in the domain of log. So this becomes log base 2 of x plus 1. That's what happens when I cancel out my common factor of x. Now, can this be simplified further? It's tempting to think so. It's tempting to think that maybe you can split this log up, but you actually can't. It really is as simple as it gets right now. All right, last two examples. Let's simplify e to the ln x plus ln y. So that's all in the exponent there. I guess I'll start by using properties of exponents. That's the same thing as e to the ln x times e to the ln y. Oh, and then each of these individually, e to the ln x is just x, e to the ln y is just y, and there we go, it simplifies to x times y. Now, number 14, I saved it for the end. It is the trickiest of all, but you can use something that we did in 13 to help you solve 14. Do you think you can see how you would solve for y? All right, I want you to think about it, but I'll go ahead and tell you. What you do is you make each side the exponent on e. So I can say e to the ln y equals e to the ln x plus ln 2. Now the left-hand side simply becomes y. That's how I extract the y out of there. The right-hand side, that's going to be like what I did for problem 13. So this is e to the ln x times e to the ln 2, and that turns into x times 2, or we usually write 2x. And there you have it. Y equals 2x. We solved it. And this finishes up Unit 12, Day 2, Properties of Logarithms. We've established 5 fundamental properties of logarithms, and we've done a lot of examples. So that's a good place to stop.